On lesson 6.3, definite integrals and antiderivatives. So remind yourself that integrals are really area under the curve, right? Area between the curve and the x-axis. So it is basically a numerical value. It is a number. All right. So what can you do with numbers? What can you do with area? You can add and subtract. You can multiply by a number, right? You can enlarge an area, but you cannot multiply two areas together, right? So think in terms of adding and subtracting. If you're adding, you can add a square to a triangle, hence making a house, right? So you're adding the areas together. You can subtract area, so you can have like figuring out the donut, so a circle within a circle, so big circle minus little circle. You can multiply the area by a number, so you can say I want twice as much area as what I have here, so you can multiply it by 2, but you can't say I'm going to take a triangle, multiply by a rectangle, right? So that is something you cannot do. So with our integrals, we can add and subtract, we can multiply by a constant, but we cannot add, we cannot multiply two integrals together. We can also combine two areas together of the same function. So in this case right here, in this particular case here, it is saying that you can take an area, here's your function, right? And forgive me for using this space here, but I'm trying to say that here is your graph and here is your function, right? If I'm saying, hey, let's look at it from B to C, and I'm going to add A to B to it, so A to B to it. Really, I'm looking from A to C. That's why you say A to B plus B to C is really taking out the middleman of B is really A to C. That's an important concept to know, because sometimes our functions are arbitrary. They're like pretend numbers. So we don't actually have a function that we're working with. And so this idea is very helpful to us because we can actually shrink down two functions that are unknown to us into just one function that's unknown to us. Okay. All right. So let's move on to this and see what we can do. So first of all, it says, I want to do negative 2 times f of x dx. Remember what I said before, you can always take out your coefficient. So that's really 1 to 9 f of x dx, like so. And that you can see this piece right here matches this piece right here, which is equal to -1. So this is really -2 times -1, which is an area of 2. Okay. All right. Next piece says, I want to look at the integral of 7 to 9 of f of x plus h of x. So you can split it. You can split integrals just like we did with summations. You can split it so it's 7 to 9 h of x dx, like so. Now you can look at this and say, all right, well, this piece right here is equal to 5. So that's 5. And this piece right here is equal to 4. So plus 4. So my total area is 9. Okay. Same thing, you can subtract with a scalar in front, so we can pull the coefficients out. So if you want to look at this, this is really 2 in the front. Integral 7 to 9 f of x dx minus 3 integral 7 to 9 h of x dx. And now I can replace this piece with 5 and replace this piece with 4. So this is really 2 times 5 minus 3 times 4, which gives me 10 minus 12 to get -2 for my final answer. Okay. All right. So what happens when your numbers are swapped? So there's a formula up here that says, hey, if you want to swap your numbers from B to A, switching it to A to B, you simply make it a negative. It will switch your numbers around, kind of like a algebra function we had early in Algebra 1. So since the function I have is 1 to 9, but this one is 9 to 1, I simply need to put a negative in front to flip it from 1 to 9 f of x dx. And so that becomes negative of -1. This becomes a positive 1 for my final answer. Okay. All right. What about this? I want 1 to 7. How does that happen? If I want 1 to 7, what I can do, first of all, which function am I dealing with? It says I'm dealing with f of x. So I'm only dealing with this one and this one. I'm not dealing with the h of x. Now, looking at the information I have 1 to 9 and 7 to 9, but I want 1 to 7. So think in terms of how arbitrary this can be. So if I'm looking at it as an area under the curve, here's my f of x, right? I have the information from 1 to 9. I also have the information from 7 to 9. So can you see that really I'm just taking my 1 to 9 and subtracting, oops, not all of it. I'm taking my area from 1 to 9 and I'm subtracting this piece of 7 to 9, and that'll give me 1 to 7. So we can do this by saying I want the integral from 1 to 9 f of x dx and subtract the integral from 7 to 9 f of x dx, and that will give me the area of 1 to 7. Now let's look at the numbers up here. 1 to 9 is a -1 minus 7 to 9 is a 5, so my area is -6. Remember, stop thinking of area as a positive number. This just means that most of my area is below the x-axis in this picture, okay? All right, next one, my numbers are swapped. So what I'm going to do is I'm actually going to swap the numbers first before I do any of the replacement of my integrals. So what I'm going to do first is I'm going to put a negative in front, make it 7 to 9 h of x minus f of x dx, right? And then I can go ahead and distribute if I want to. There's many ways to do this. It's really kind of up to you. So if I do distribute the negative inside, it becomes negative h of x plus f of x dx. Really, this is saying, sorry, let me redirect my work. This is really saying the integral 7 to 9 of f of x minus h of x dx. Right, so that's a lot easier to work with. So now I can rewrite and say, all right, this is really 7 to 9 f of x minus 7 to 9 h of x dx. Don't forget my dx. All right, so the first one, I can replace that with a 5. And the second one, I replace that with a 4. So my final answer is 1. Okay, lots and lots of ways to do this. You could go ahead and work it out and then swap the numbers, or you can just you can switch the order somewhere along your work here, but lots of ways. Okay. All right, so there's a mean value theorem here. Again, we had a mean value theorem back in derivatives. So there's two mean value theorems. They're both called MVT. One is the MVT for derivatives. One is the MVT for integrals. The MVT for derivative is when you are equating the instantaneous velocity with the average velocity. So you're taking the derivative, setting equal to the slope, to the y2 minus y1 over x2 minus x1. Here in this case, this is saying I am looking at an area under the curve, right, as a number, and I'm looking for the average of it. So that you need to multiply by 1 over b minus a to find the average, right? It's almost like GPA, for example. You add all your grade points up and you divide by how many classes you're taking. So that's the idea, that this is the whole points and divide by how many classes you're taking to find the average, okay? All right, so if we take a look up here, it says find the average value. At what points the value does the function assume its average value? So you got to look for the average first, right? So the average would be, if I follow the formula, the average will be 1 over 3 minus 0, because that's my integral of 0 to 3, negative x squared over 2 dx, right? So we can go ahead and work this out. This is 1 over 3. This is, don't let this confuse you. This is really negative 1/2 x squared, right? So I can pull the negative 1/2 out. Remember I said any coefficient can be pulled out really nicely. You have x squared dx, 0 to 3. So it's negative 1/6. Now go ahead and take the antiderivative. Get x cubed over 3. You value it 0 to 3. So negative 1/6. Plug in the 3. So you get 27 over 3 minus 0 over 3. So you get negative 9 over 6, which is negative 3 over 2. Okay, that is the average value. So now it's asking at what points does the function assume the average value. You then go ahead and take your original function, your y equals negative x squared plus 2. So negative x squared plus 2, and set it equal to this average value. It's the same idea as derivatives too, where you're setting one equal to the other. So, right, so you're telling me at what value will this happen? Okay, well, since they're both over 2, I can ignore the denominator and make it negative x squared equals negative 3. Divide by negative 1 on both sides, you get x squared equals 3. So x equals both positive negative root 3. And then you're looking at your interval and you notice that, oh, well, it's in the interval of 0 to 3. So my value is just positive root 3. So positive root 3 will be where my average value will occur. So another way to look at this is, what I tell students is that you can look at this as the area under the curve and where you're making the cut, so that you get an average piece. It's kind of weird, but that's kind of the idea of it. So my cut is going to be made at x equals root 3. So when I cut it there, that piece I'm getting is the average of the whole thing. Okay. All right. Same thing, same setup with the next one. I always set up by figuring out the average first. So it's 1 over 3 minus 0. And by the way, the intervals just happen to be the same thing here. Integral 0 to 3, x minus 1 squared dx. All right. A few things. I don't have a product rule, so I need to work this out. I need to expand this out. So this becomes x squared minus 2x plus 1 dx. And then keep your 1/3 outside. Go ahead and now take the antiderivative. You get x cubed over 3 minus x squared plus x, evaluated 0 to 3. Keeping the 1/3 outside, again, it's much easier to work out this way. I get 27 over 3 minus 9 plus 3 minus 0. You know, you plug in 0 to polynomial functions, you're going to get 0 all the way, right? So you get 1/3, you get 9 minus 9 plus 3, right? And you get 0 plus 3, which is 3. So 1/3 of 3 is 1. Okay, now we need to take my original function of x minus 1 squared, and set that equal to this average value of 1, and see when will that happen. Okay, first you want to take the square root, so you get 2 answers. You get x minus 1 equals plus and minus 1. So now you got to set up 2 equations for solving this. You get x minus 1 equals positive 1, x minus 1 equals negative 1. You add 1 to both sides, you get x equals 2, and x equals 0. All right, so yes, both of these are in my interval, but it's not useful to me if my number is right on the edge of my interval. So my x equals 0 is extraneous in a sense, and so my final answer would be x equals 2 is where my average would occur. Okay? All right, last problem here says find the average value of the function on the interval without integrating by appealing to the geometry of the region between the graph and the x-axis. So it's asking you to use geometry, right? So the average value, let's set up our formula. The average value is equal to 1 over b minus a, so 2 minus negative 4, the integral of negative 4 to 2 of f of x dx. So this is 1 over 6. Well, this is what you're appealing to the geometry of it. This piece of it is the area between the curve and the x-axis, and f of x is defined here. This is the area, so I'm looking for the triangle, right? So I'm taking the area of a triangle, so 1/2 base is from negative 4 to 2, so 2 minus a negative 4, that's base of 6. And then the height is 3 right here. You can plug it in, or you can look at the graph here. So that would be your area of the triangle. So you get the average 1/6 times 3 times 3 is 9. So the average value here is going to be 3 over 2. It's not asking me when the function is going to occur, so all I have to do is find the average, and I end my piece here. Okay? All right, make sure you do practice the problems with your homework, and that's it.